No it don't! No it don't!
I've taught you how to find the area under the curve. Area under curve. Under the curve. Okay, that was pretty easy. But now the question lies, see, this is 2D. Everyone can work with 2D because 2D is pretty simple. But we live in an age where everything is 3D. There's a new Oculus Rift coming out by Facebook. It's a virtual reality thing coming. That's 4D. But now we want to just work with 2D. If I want to work with 3D, see, 2D is area. That's what I can ask you. If I work with 3D, I'm going to ask you for something else besides area. Guess what I'm going to ask you? I'm going to ask something called volume. Area is easy because that's 2D. The 3D is going to be volume. Now here's how I'm going to teach you 3D. There was a formula for a sphere. Does anyone remember the formula for a sphere? So to make this 3D, so let's make this 3D right now, and I can easily make this circle into 3D by adding a bunch of shades to it, and it becomes like a little. Let's just add a little, so it's like floating in the sky. So now that looks pretty cool. That's the sphere now. Okay. I say, hey, Miss Noah, you're pretty cool. Hi. So now I have a 3D object. Volume. You probably learned this in grade 10. Anyone know the formula for volume sphere by any chance? 4/3 is correct. Keep going. Pi r cubed. Correct. But the question is, where did this formula came from? Where did it come from? So I'm going to say, Miss, no, that's easy. The textbook, my teacher told me. But the question is, I want to actually go back and see, analyze this. Where did actually this arise from? Where did it come from? So this formula actually came from calculus. I'm going to show you how to derive the formula. So all the formulas you have been memorizing, there's a way to get the formulas. Here's how we do this. This goes back to my little video I should show you, concept of tomato cutting. If I were to think about this, would you agree that this is a 3D object? It's very simple, it's 3D. But if I were to take a little knife and I were to cut a super razor thin piece, so we're going to chop this up. Say we're going to chop a super duper thin piece, very thin. If I were to chop an extra thin piece, would you agree that what I get is I get a perfect circle if I did it correctly? So if I were to do it very thin, I get a 2D shape, which is a 2D shape of a circle. So if I were to take the knife and cut up this tomato into super duper thin slices, it actually be 3D, it actually becomes 2D. So when I was showing you this video right here, where did my tomato go? See, when the guy chops it, it actually becomes a super duper thin piece. But if I actually have a sharper knife and I cut it even thinner, what you really get is just a simple 2D shape. And the area of this, area of a circle, would you agree, is pi r squared? Because it's the area of a circle. Most shapes you're going to work with will work with something called circle. So we call this the cross-section area. Cross-sectional area is a circle. So the cross-sectional area of a sphere is really a circle. So to find the volume of this, would you agree that if I add this circle, so let's draw about 4 of these. 1, 2, and again, I'm going to assume they'll try to be the same shape and size. If I take a very thin slice, area 1, and I plus area 2, plus area 3, plus area 4. My question is, how many thin slices will add up to this tomato? How many thin slices, Jana, how many thin slices will add up to the tomato? It's an infinite. Because really, I can take as thin as I can, but if I take all these infinite slices, it will form my perfect tomato. And if I think about that, that gives me something called volume. Agree? Infinite area gives me volume. That's what volume really is. Volume really is infinite area. A lot of people don't realize that. So I can rewrite this formula as volume equals to lim n approaches infinity of sigma I equals to 1 n a x I delta x. You've probably seen this before. When I say all this is saying is this, I'm going to add all the areas up from 1 to infinity. But instead of writing all this stuff up to infinity, I can use integrals of a to b, ax dx. So which means if I take the integral of area, what I'm left with is volume. That is the main concept. So put a bubble around this. And again, it goes back to my Japanese knife idea. Volume really is integral of area. I'm going to show you how I'm going to apply this. We're going to go back to my circle question last about where that formula came from. I want you to get some practice. Try this one. It's going to say find the volume. Find volume of a solid obtained by rotating about the x-axis the region under the curve y equals to root x from 0 from 0 to 1. I'm going to show you how to do this because this is your first time. It says find the volume of a solid obtained about the x-axis, the region under the curve y equals to root x. First thing you're going to do, you're going to sketch out y equals to root x for me, please. You need to know what is a rough sketch. So if I were going to show this, it looks something like this. 0, 1. 0, 1. Here's what the question says. We're going to take this line, we're going to rotate. So I'm going to spin it this way, about the x-axis. Highlight this for me, please. About the x-axis. So we are going to rotate it on this axis right here, which means I'm going to spin it really, really fast. And when you spin it really, really fast, it looks like you're going to form a little vortex, like that. So if I spin it really, 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 really fast, you're going to create a little cone or a vortex, like that. So draw this in right now. So here's the region under the curve, right here. That's the region under the curve. I'm taking this region, I'm going to rotate about the x-axis really, really fast. When I do, it creates a cone. What they're asking you is, what is the volume of this cone? What's the volume? So here's how we're going to do this. In order to find volume, you need to know what one area looks like. So imagine you have a super sharp Ginsu knife, and you're going to chop this up. We're going to cut this up. If I were to cut this up right here, what would the shape look like? Okay, so I'm going to chop it up. What would the cross-sectional area look like? Now, Rosa, what shape is it? You get a little circle like that. Okay, I drew like a square, but in reality, you get a little circle. So let's find the area of the circle. Area of a circle, most of the time for this chapter, you're going to work with circles only. You get pi r squared. Here comes the hard part. Pi is easy. Pi is just pi. So we know it's the integral. It says from 0 to 1. 0 to 1. Of my area. Area. I don't know what my area, that's what I'm going to figure out A. So area is pi, which is pi. The biggest question is, what is R? And this is where you come. See, here's the trick. R, which you agree is from here to here. That's R. That's R. Well, in this case, that value right here, that equals to root x. That's the concept a lot of people don't understand. See, if I were to cut this circle up, R is the radius. The radius is from here to here, which is root x. So then this becomes root x squared. So would you agree, then this becomes 0, 1. This becomes pi x dx. And that's my volume. Take a look at my work from beginning to end. If there's any issues, now's a good time to ask. Go ahead, solve it. I'm going to...
There's like, yeah, there's mist and then there's like...
So, guys, settle down. If you did this correctly, you should have pi x squared over 2, 0 to 1. I'm not going to go through the whole process of subbing in, but your answer really is pi by 2. That's called volume. Because why? I take something, I rotate it, and it goes back to the tomato example. It goes back to the very basic principles. Try this one. Again, nothing too bad. What if I were to twist it up a bit? And I will say, find the volume. This is where it gets a bit tricky. Of the solid. And again, I'm going to tell you this right now. Everything you're going to do is all based on circles for now. Of the solid obtained by rotating. Obtained by rotating about the x-axis for the region enclosed by y equals to x and y equals to x squared. First thing you should highlight is this. I'm focusing on the x-axis again. Draw a diagram and figure out what is tricky with this question. Have fun. I'm gonna rotate this, but before I can rotate, I want to draw a diagram. Y equals to x and y equals to x squared looks something like that. So what they want to know is, what does this look like if I were to rotate it on the x-axis? So here's what I'm going to do. I'm going to rotate this on the x-axis, and it's going to look something like this also. So my shape, would you agree, looks like a ring. Hi, redo? Okay, let's redo. Okay, so watch what happens. So this blue region, agree? I'm going to rotate this blue region really quick. When I do it really quick, it's going to form a duplicate down here somewhere. Agree? But if I were to watch the whole process, what is going to form is you get a double ring, because each line creates one circle. Agree? since I have two lines, I have really a circle inside a circle. So this is your, think of this as a hollow cone. Sorry, circle in a circle. Because each line creates a circle in a circle. In a circle. The question is, so what I'm really after is the area of this red circle. That's what I'm really after. I want to know the area of the red circle. Because this straight line creates the outer circle, agree? Because each line creates a circle if you rotate it really, really quick. This curved line creates an inner circle. Should be right here. So therefore, what I want to know is the region bounded, which is the red piece. So I know that right off the bat, it's going to be integral of this area. But in this question, I didn't give you my boundaries. So guess what you got to do? You got to figure out your own boundaries. What are these things, first of all? And you do this by graphing it. You can easily graph this out, or you can use algebra and solve it. And if you use algebra, I believe you should get 0 and 1. Okay. If you use algebra and you solve it, you should get 0 here and 1. But more importantly, what I'm really after is the area. The area is given by, so I think about this, I have two areas, area 1 and area 2. Because there's two circles. I have the big circle and the small circle. Area 1 is pi r squared. Area 2 happens to be pi r squared also. But I'm going to use the subscript 2. What is the real area going to be? Go. Figure this one out. Think about it. Would you agree it's going to be pi? Now the big circle is created by this top line because it's the region of this curve, which is pi times x. The other circle, pi r squared, which is pi x squared. The other circle, go ahead and write down the other circle for me. I'm going to pause it. And if you did the right, I believe you should have pi x squared to the power of 2, which becomes pi x 4. Because, let's go back to here. I'm going to zoom in here. Would you agree the outer circle, let's use green, is from here to here. This is the first circle. This is R1. Okay? R1 is just equal to x. Because y equals to x. Because the y value equals to R2 is the distance from here to here. That's R2. So R2 is the distance from here to here, which is x squared. So now the area is 0 to 1 of the first circle, pi x squared minus pi x 4. I can rewrite this simply as 0 to 1. I can factor the pi. X squared minus x 4. I'm going to pause it. You can actually solve on your own from here, and if you did it right, you should have 2 pi by 15. That is how we do it. This is the same thing as saying, what's the area of the region enclosed? So I'm going to draw this again a bit more clearly for you. If I just look at this piece right here. Karan, question? Oh no? If I look at this piece, the true thing is, if I want to get this piece right here, I take all the area of the line minus area of the curve. And that's what I did here, which is x minus x squared. Okay. Just from yesterday's lesson. My question now, last question for today is, what happens when you rotate in the y-axis? How do you rotate in the y-axis. You got to be careful how I'm asking you to rotate, because it's crucial, because you change a lot of things. Try this one. Find the volume. Find volume of region bounded by y equals to x cubed, y equals to 8, x equals to 0, and you're going to rotate about the y-axis. So if I were to rotate this in the x-axis, everything is in x, see? All in terms of x. If I were to rotate in the y-axis, everything has to be in terms of y. This is the first crucial thing. So notice y-axis. So everything in terms of y. Terms of y. Sorry? Y equals x cubed? X equals to 0? If x is equal to 0, what's the value of y? 0. Because I sub into here. So you got to learn how to convert back and forth. So guys, why don't you try this one? I'm going to put strings. I have to show you how to quickly do this. Notice everything is in terms... Everything is in terms of y. So if everything is in terms of y, I look here. I can't just simply plug in x anymore. I have to isolate for x. So x equals to cube root of y. Because I just said everything has to be in terms of y. So if I were to do this, then this now becomes 0, 8. Okay. This becomes y cubed. And notice I'm using dy. If I were to draw a graph, your graph for this would actually look something like this. It looks something like that. So what they want to know is, what is this region right here if I were to rotate in the y-axis? So if I were to rotate in the y-axis, it will create a cone looking like that. Looks like a cone, a tornado, whatever you want. So in this case, r is right here. That's your radius. Your radius is really cube root of y. And that's why it's going to be, so I forgot there's a pi here. Pi, so this is equal to r. So this is pi r squared. Which I can rewrite this as pi 0, 8 y 2/3 dy. And you can easily solve it from here. Because if I rotate in the y-axis, your radius now is this piece. I'm going to quickly give you the answer. If you did this correctly, you should have 96 pi. And you can actually go home and try this on your own. 96 pi by 5. But your work! Page! Oh, you can actually bring this on your boat cruise and do it. One hand on the calculus book, the other hand on your calculator. 387, numero. 1 to 10, that's it. Oh.